Welcome to solverfy.
So we have a cylinder of radius r1 and a cylindrical shell of inner and outer radius r2 and r3. Now we want to find the field in the various regions. First of all, if you've done the previous problems, you will remember that the electric field due to a cylinder is of the form Q enclosed divided by 2 pi epsilon naught r L, where r is the radial distance from the cylindrical source. L is the length of the cylindrical source, and Q enclosed is the charge enclosed within your Gaussian surface. Now, for part A, consider a distance less than r1, that is within the inner cylinder. So, electric field is Q enclosed divided by 2 by epsilon naught RL. Now, Q enclosed is simply the charge density times the volume, and the volume is simply pi r square times L divided by 2 pi epsilon naught RL, giving us rho r by 2 epsilon naught. And remember that the charge densities in both the cases are same. So for part B, you are in this region, in between the two cylinders. So the charge enclosed is always the same. Here, E is equal to charge, the same formula. But here, the charge enclosed is simply rho times the volume of the cylinder, which will be pi r1 squared times L divided by 2 pi epsilon naught RL, giving us rho r1 squared by 2 epsilon naught R. For part C, we want to consider in between the outer cylindrical shell. So your Gaussian surface looks something like this. So when this is the case, obviously the charge enclosed will be rho times the volume of the inner cylinder, which is pi r1 square L, plus the volume of the cylindrical shell that is inside the surface, which will be pi r square L minus pi r2 square L, where r2 is the inner radius and r1 is the radius of the inner shell and r3 is the radius of outer radius of the shell. Therefore, electric field is rho into pi L times r1 square plus r square minus r2 square divided by 2 pi epsilon naught RL, which turns out to be rho by 2 pi epsilon naught r1 square plus r square minus r2 square by r. For part D, we want to consider outside the whole cylindrical shell. So in this case, the charge enclosed will always be the same. Hence, electric field will be rho times the volume of the inner cylinder, that will be pi r1 square L, plus the volume of the whole cylindrical shell, which will be pi r3 square L minus pi r2 square L divided by 2 pi epsilon naught RL, which turns out to be rho into r1 square plus r3 square minus r2 square divided by 2 epsilon naught R. Now, it is very hard to show you plots, but you can simply put this piecewise function into any plotting software and substitute the numbers. But I can show you how it roughly looks. You are asked to plot until 20 meters, and at 5, 15, and 5, 10, and 15 meters, the nature of the graph becomes different, has different formulas starting at these points. The field initially increases linearly and then falls as 1 by r, then increases sort of linearly and then falls off again as 1 by r. The fields should be of the order of 10 power 4 Newton per Coulomb, where the maximum point should correspond to about 8.2 into 10 power 4 Newton per Coulomb. This is how your final graph will look. Your x-axis will be r in centimeters and y-axis will be electric field in 10 power 4 Newton per Coulomb.